Okay, question number 3. So this is on for Wednesday. Okay, let us begin with this. This is for 11 marks. Let me start this timer. Okay. An experiment to investigate the simple harmonic motion consists of a mass oscillating at the end of a vertical spring. Okay, so you have a mass, your spring connected here, and this is going to oscillate up and down like this. Okay. And then below this script is a motion sensor which detects what is the motion of the object, whether the object is coming nearby to it or not. The mass oscillates vertically about a motion sensor that measures the speed of the mass. It measures the speed of the mass. Test 1 is carried out with a 1 kg mass. You put a 1 kg mass and you make it to move like this, and spring of spring constant K1. Okay. Test 2 is repeated with an experiment with a 4 kg mass and a spring of spring constant K2. So you use 1 kg mass with spring constant K1, and you use K2, a different spring, and a 4 kg mass. Okay, and you make it to oscillate, and you are going to find out what is the distance or whatever parameters this motion sensor will do it. Okay. The variation with time of each speed of the vertical speed of the masses for one cycle of oscillation is shown. Okay, vertical speed. Okay, variation with time. So what is being shown over here? It shows what is this here speed in meters per second, and test 1 and test 2. What are test 1 and test 2? Test 1 is nothing but you have masses. Let me put my picture here. Okay, so you have masses here. This is for 1 kg, and this is for 4 kg. This is what you got as test 1 and test 2. Okay. Now what has been asked? Calculate the frequency of oscillation for both the tests. Frequency of oscillation. Since it's a plot of time period versus the speed over here, frequency should not be difficult. What is the frequency here? The time taken between one max and the other max. See, though the amplitudes of this velocities are different, but this time is one and the same for both test objects, right? So what is the time taken? Starting from here to here, it is 0.8 seconds. What is this now? Time period t. Let me write it down there. What do we need? We need frequency. Time period is given as 0.8 seconds from the graph. Frequency is 1 by time period, which should be 1 divided by 0.8. Let us find out what is 1 by 0.8. 1 divided by 0.8 is equal to 1.25. 1.25, what is it? Hertz. But since we have only two decimal points over here, so you can say 1.3 hertz over here. 1.3 hertz. Okay. Next, K1 by K2. K1 by K2. What is K1 by K2? Spring constants. Now, what is K1? How is K1 related to any of the parameters? K1, where do we use K1? F is equal to minus Kx. That is where you use this, right? Okay. And if I take F equal to M into A, which is equal to minus K into X, A should be equal to minus K divided by M into X over here. And this is what we consider this as minus omega square into X, right? So therefore, we know that K by M is equal to omega square, or K is equal to M omega square, which is standard derivation. We already done so many times in the classroom also. Okay. So therefore, if I take K1 by K2, I will have M1 omega 1 square divided by M2 omega 2 square. What is omega 1 and omega 2? The frequencies, angular frequencies, and omega, as we know, which is nothing but 2 pi into F. Okay. 2 pi is a constant, F is the frequency. Now let us look. Does the frequency change for both test A and test B, test 1 and test 2? No. Time period is same, frequency is same, which means that F1 is equal to F2, or omega 1 is equal to omega 2. When omega 1 is equal to omega 2, this cancels away and you get M1 by M2. What is M1 by M2? What is M1 is 1 kg, M2 is 4 kg. So this should be equal to 1 by 4, which should be 0.25. Okay. Let us move on to the next one. Determine the amplitude of oscillation for test 1. Amplitude of oscillation for test 1. What is given here? For test 1, what do we know here? Look at the graph here. This is nothing but 5, right? This 4, 5, not even 5, I say. This is 4, 4.2, 4.4, sorry, 4.2, 4.8, 5.2, 5.66. Okay, it should be 4.8 then, not even 5, 4.8. 4.8 meter per second is the maximum velocity for test 1. That's what is known to you. Okay, let us go back to this. So from the graph, we have Vmax for test 1 is equal to 4.8 meters per second. Now what is he asking? Amplitude. How do you find amplitude? We know that Vmax is equal to amplitude times omega, right? Now Vmax is known. Now what is amplitude? Omega. Omega is nothing but 2 pi f, I already told you that the answer, the clue for the input for the second question will be the answer from the first question, right? So we already got the value of f here. Where is it? F is equal to 1.3 here, right? So let us substitute this. So therefore this should be 4.8 is equal to a into 2 into 3.12 multiplied by 1.3, or the value of a here is equal to 4.8 divided by 2. It is 1.4, 3.14, sorry, 3.14 multiplied by 1.3. Now let us do this. What is the value I get? I get this as 4.8 divided by 2 is equal to so much, divided by 3.14 is equal to so much, divided by 1.3 is equal to so much, 0.5879. First let me write down the full value, then I will simplify it. What is this? Meters, or I can now write this equal to 0.6 meters. This should be your answer. The next, in test 2, the maximum elastic potential energy stored in the spring is 44 joules. Maximum elastic potential energy. Where do we get maximum elastic potential energy? You get maximum elastic potential energy only at the extremes, E1 and E2. Because when at the mean position, kinetic energy would be more, potential energy is lesser. Okay, so therefore this is what we get. At t equal to 0, the value of the potential energy for test 2 is 0. Okay, so here E mean is equal to 0, potential energy is 0, right? Sketch on the axis the variation with time of EP for test 2. EP for test 2. Again, okay, when he is giving you so much, we need to look at, okay, what do we derive information from the graph. Now let us go back to the graph for test 2. What is that? What is the special thing here? See, maximum speed is here, 10 meter per hour. This is how much is it? This is 8.4, 8.8, 9.2, 9.5. This value is around 9.5 or 9.6 could be. This is 9. This should be 9.6, right? Let me calculate it once again. 8, 8.4, 8.8, 9.2. This should be 9.4. I'm sorry. This should be 9.4, 9.6, 10. Right, 9.4 meters per second. And what is the frequency? Frequency is 1.3 hertz. And let us look at this here. The velocity becomes 0 at 0.2 and 0.6. Let us write down all this which is given to us, right? So we have V max is equal to 9.6. I do not know whether it will be useful or not. And then we have V minimum is equal to 0 at t is equal to 0.2 seconds and t is equal to 0.6 seconds. This is what we know. Okay, now what we do is at t equal to 0 seconds, he already says potential is 0. At t equal to 0, potential energy is 0. We already put this point. Now, then what happens? At t is equal to, what is the total time period? Total time period. Let me go back to total time period. Total time period is 0.8 seconds. Okay. So when kinetic energy becomes 0, now we have got some clue here. See, when kinetic energy becomes 0, potential energy is maximum. When can kinetic energy become 0? When either mass should become 0 or velocity should become 0, because kinetic energy is half mv square. M cannot become 0 because mass is always there, right? V can become 0. Now when will V become 0? At t equal to 0.2 seconds, which means at t equal to 0.2 seconds, potential energy is maximum, right? So potential energy will be maximum at t equal to 0.2 seconds. What is that value? The value is 44 joules, right? The maximum elastic potential energy is given. Okay, at t equal to 0.2 seconds, it is 44 joules. So this is 40, this is 42, 44, 46, 48, 50. So this should be 44. I'll mark one point here. In a similar way, at t equal to 0.6 seconds also, it is 44. T equal to 0.6 also at the same point over here. Okay. And again, the potential energy becomes 0. Where does potential energy become 0? Potential energy equal to 0 at t equal to 0, and also it becomes 0 at t is equal to what? At t equal to, see, whenever velocity is maximum, potential energy becomes minimum. Where does velocity become maximum? Once again, where does velocity become maximum? Let me go back to this. See, because it gives you a chart of velocity maximum. So velocity is maximum at this point at t equal to 0. Velocity is minimum at t is equal to, what is this value here? This is minus 10 minus 9.6 minus 9. So this value would be minus 8.4, 8.8, 9.2, 9.2, and this value would be 9.6. In between 9.2 and 9.46, where is it? 9.4. Okay, so it is at 9.4. So let me go back to here, and at t equal to 9.4. No, velocity. What am I checking here? I need to look at when will it become 0. I am looking at what is the velocity at that point. It is becoming 0 at this point, which means what? At 0.4 seconds. Let me go back once again. At t equal to 0.4 seconds, the velocity becomes maximum. When velocity becomes maximum, potential energy becomes minimum. So at these points, velocity, potential energy is maximum, velocity is maximum. Velocity is maximum, potential energy is minimum. So we have got 4 points. Now what we need to do? We need to do a graph. So join this smoothly like this. Smoothly like this. This comes like this. This comes like this. And once again it goes like this. And this comes like this over here. Sorry. This comes like this over here. That's it. Okay, time is also up. Anyway, we were able to complete the graph. So how many marks is this? This is for 2 marks. What do we expect? We expect 2 peak points properly written, and we expect 2 nodal points properly written, and this should be a smooth curve like this. So these 3 points are very important to draw a graph. Okay, we have drawn this. The question is a little bigger. Okay, we cannot finish in 10 minutes. Right. The motion sensor operates by detecting the sound waves reflecting from the base, the mass. The sensor operates the frequency, compares the frequency detected by the frequency emitted when the signal returns. So what is this motion sensor? How does it do? How does it actually detect? It is not like our eyes. Our eyes would be able to see something. But what it does is, it will have an infrared sensor. So it will be having a source. The source will send some signal, okay, and it will get reflected from the obstacle, come back to me, and I will find out what is the time taken by it, and thereby I will say, yes, this is what is the distance the object is at. Okay. Now the sound frequency emitted by the sensor is 35 kilohertz. That's what I said. It is emitting a 35 kilohertz signal. It goes to the obstacle, comes back to me, and then I can find out what is the distance. Right. The speed of the sound is given. Determine the maximum frequency change detected by sensor for test 2. What is the maximum frequency change? Now what can happen? Now what's happening is, let me write down the diagram. So this is the spring, this is the object, and this is the sensor I have kept. Now this is sending some signal. So this mass, if it is nearer here, then the signal will travel a shorter distance and come back here. So therefore, it will get some time period. It will take them some time period, and based on the time period, you can find out distance. But the interstellar is not finding distance. Okay, you will get some time period. It will take shorter time for the wave to start from here to reach here. Now, if the object is at this, okay, this is complete expansion. This is expansion of the spring. This is complete contraction of the spring. Okay, this is the mean position. Okay, I'll write down if you want. Mean, this is your contraction, this is your expansion. When it is contraction, what happens? That the signal has to travel all the way along to there and come back. Okay, so therefore, now let me do this in a different way. So what is the different way here? Different way is that, let me assume if there was a sensor here. Okay, if there was a sensor here, and you are emitting the source, you are the source here. Source, and there is a sensor here. Now, when the object, this is the observer. Okay, you can call this as an observer. The observer has a sensor and he is approaching the source. Now, what is this effect? Doppler effect, right? In a Doppler effect, what happens? The frequency that the observer hears, because he is moving towards the source, is given by f dash is equal to c divided by c minus vs. I can write like this: c minus v naught divided by c minus vs into f naught. Now what I do is, let me assume that the observer is stationary and this source is moving towards it, relative, right? I can take it anyway. So what I do is, in that case, if observer is stationary, because easier to understand, so I can write f dash is equal to, I'll put 0 divided by c minus vs. Now what do I do at vs? Vs is positive as it moves towards it. Now what is the velocity? The maximum velocity I will take. What is the maximum velocity here? We already found out what is the maximum velocity here. What is the maximum velocity? I wrote this as 9.6. Where did I get from? I got it from here. See, I got it from here, right? So I have written 9.4 here. This 8, 8.4, 8.8, 9.2, 9.4. Sorry, 9.4. I take this as 9.4. So I'll write this as 9.4. So divide my 9.4 multiplied by what is the actual frequency? 35 kilohertz. Now what is C? Not velocity of light, speed of sound. So therefore this will be 340 divided by 340 minus 9.4 multiplied by 35. Okay, now let us calculate this. So this will now be equal to, let me use my calculator. So this will be 340 minus 9.4 is equal to 330.6. I'll write this as 330.6, and this is 340 multiplied by 35, which should now be, let me calculate this, this will be 340 divided by 330.6 is equal to so much multiplied by 35. When I do this, I get 35.995. 35.995, which is nearly 36 kilohertz. Which means what? When the mass is coming like this and you keep the sensor here, then the frequency recorded by the sensor is 36 kilohertz, which means there's a frequency shift of 1 kilohertz when the sensor is considered to be present here. But if I consider sensor to be here, which means what? The rays, the signal has to travel this distance, it gets a shift of 1 kilohertz. When it has to reflect back, it has to get 1 more kilohertz of shift, which means the total shift here should be 2 kilohertz, right? The total shift should be, so this is your delta F over here. The total delta F, I'll write delta F total should now be equal to 2 kilohertz, which means the signal that you receive here, okay, because of this shifts is nothing but equal to, what was the initial? 35, and so it is coming like this and going back over here. So since coming over here, so total shift should be 35 plus 2 kilohertz, which should now be equal to 37 kilohertz. 37 kilohertz is the frequency that you should receive. Now what is this we have done? We have considered that the sensor should be at the observer's location, and as it comes down, what is the observed frequency? Okay, and then when I take that sensor and put it down to my source, then what will be my observed frequency? I observed that when the sensor is kept there, the frequency shift is 1 kilohertz, and when I keep it here, the same 1 kilohertz I will add it up over here and I will say 2 kilohertz. So thus you observe the total frequency shift should be equal to 2 kilohertz. So thus the original frequency will get added to this, and thus you get 37 kilohertz is the final frequency. What is this we have done? We have done only for the motion of the object, the mass, when it is coming down. Now who will do it for motion of the object when it is going down? I myself have to do it, right? Now let us do that also. So now what is happening? The first part is done. Second part, the spring is now here. The object is going up like this, and this is my sensor. This is my sensor. Now in this case what happens? The observer is going away from it, right? Now your F dash will now be equal to C minus V0. V0, observer is moving, divided by this Vs I will consider 0. Okay, C divided by F naught. When I do this value, so what do I get here? This will be 340 minus 9.4 divided by 340 multiplied by 35 kilohertz, which will now be equal to, let me do this, 340 minus 9.5 is equal to 330.5 divided by 340 is equal to so much multiplied by 35 will be equal to 34. So you get 34 kilohertz. So what did I do here? Again the same logic. Okay, I consider that the sensor was kept here on the observer's plate, and then the sensor is now moving away from the source. Okay, this is your sensor. The observer is moving away from the source, and as a result of it, the observed frequency is 34 kilohertz, or the shift in frequency is seen to be 1 kilohertz now. 1 kilohertz when the sensor is kept here. But when the sensor is kept here, then what will happen? The new frequency now will be 2 kilohertz. 2 kilohertz. That means the shift in frequency is seen to be 2 kilohertz, which means the actual frequency will now be 35 minus 2, which is equal to 33 kilohertz, right? It is 33 kilohertz. Now what is being asked? Determine the maximum frequency change that can be detected by the sensor for the test 2. The maximum frequency change that can be detected is If it is going upwards, it is 2 kilohertz, 2 kilohertz. And if it is coming downwards, so if it is going upwards, it's 2 kilohertz, downwards also it is 2 kilohertz. Thus 2 kilohertz should be your final answer. Don't write this as 2 kilohertz minus plus 2 kilohertz, 4 kilohertz. That's not the answer. Okay, it is only 2 kilohertz. With respect to the main position, we write this. Okay, I think we have come to an end to this. Thank you.